So this is part two of the hammer throw. Let's see how far the hammer throw can go downfield. What would be this distance if we know a couple of the initial conditions from like the first part that we did? So let's start thinking about how a hammer throw person throws a hammer. They start out with the hammer being like in just off the ground, and then slowly they bring the hammer into like a degree of like they want to go 45 degrees, but it never quite goes 45 degrees because that's really very difficult to do. So as the hammer person begins to throw this thing around, they actually, if you watch them, they actually bend their bodies. They don't throw it straight up and down. Like they're not throwing the ball like perfectly straight up and down. They're actually, their body's kind of bent, and when they bend their body, the ball rotates around that body, but that rotation is not always directly in line, perfectly flat with the body. It's always off by a few degrees, and it's going to be very important to find out what that is, and it's going to be very important to find out that this is not it can't be many degrees, and as a thrower, they're going to soon find out what degree is the best for the ball to go furthest down the field. You'll see here in a second. So if we assume the chain is 1.21 meters, which is the average chain size for a hammer throw, and if we figure that most arm lengths are about 1 meter, we know that the rotation that this ball is going to be taking is going to be 2.21 meters. So our R is going to be from the center of the body over here to the ball is going to be 2.21 meters from the center of the body to here. So that's going to be what it's rotating around. Now I know hammer throwers, they have to take their hand, one of their arms has to go over their head, and if you watch them as they do it, the arm does go up and over the head, but they still maintain this like 1.6 degree. It doesn't, it's not exactly in line with their body perfectly. It's kind of like just barely off. So let's think about how far down field this thing would go if the person can get about 1.6 degrees off of from their body angle. So let's think about that. So if we look, from our first video, we learned that our tension sign is going to be mg. So if we know this sign was going to be our sign of 1.6 degrees, and we know the mass of the ball, and we know the pull of gravity on the ball, we can figure out the tension of what the person's going to feel here at 1.6 degrees. So let's think about that. So our tension is going to be our sign, it's going to be equal to our sign divided by mg. I mean, mg divided by the sign. All right, so tension is going to end up being our mg, which is basically the weight of our ball, which comes to about 71.22 something newtons. So 71.2206 newtons. How did I get that? I multiplied the mass times the gravity. The mass of the ball was what? I think in the first video we said it was 7.26 kilograms, right, times 9.81 meters per second squared. You'll get this number. All right, so we know that. Now we're going to be dividing by the sine of 1.6 degrees. Now 1.6 degrees sine is going to be pretty small, fairly small, so you could start dividing by a small number. You really get a large number here, and in fact what you get is 2550 0.73 newtons. Okay, might not mean much to you, right? But let's think about that. That's about 573.427 pounds. All right, almost 600 pounds of pressure. Almost 600 pounds this particular person is going to have as they swing this ball around. It's almost 600 pounds that they're feeling at the end of that ball. And this is pretty typical for a hammer thrower to have nearly a 500-pound force being pulled on their body. So that's why this is not always an easy sport. Definitely not. So let's think about that. At this particular tension, what's going to be the velocity that's going to be needed? This is going to be a square root, by the way, sorry. what's going to be the velocity that's going to be needed to get this ball to go downfield? What's this, when it finally lets go, what's going to be the velocity of the ball? Well, let's think about that. So our velocity is going to be equal to our tension, which we've already got 2550.73 newtons. It's going to be multiplied by the cosine of 1.6 degrees. And then we're going to multiply it by our rho. Now remember, our rho is from the center of the body out here to the center of the ball, which comes to what, 3.2 or 2.21 meters. And then we're all going to be dividing that by the mass of the ball, which is 7.26 kilograms. And if you look at this, newtons, this all divides out into meters squared, or yeah, meters per second. So our velocity is going to be equal to about 27.86 meters per second. 27.86 meters per second, which is really nice because when I Googled and looked up what's the average is close to 30 meters per second. That the average person that goes into whatever they're doing with the hammer throw is usually about almost 30 meters per second. So we know we're pretty close here. And it's amazing that it's almost 600 pounds that person is experiencing as they throw that thing around. Well, now we know our missile velocity. That's the thing, when they let it go, this is the velocity they're going to let it go at. Oh, well now, since we know that, since we know this velocity and we know the tension, we can figure out with the range formula how far it goes downfield. Let's just do that real quick. All right, I'll let you take a picture. 1, 2, 3. If you'd like to, you may take a picture. Okay, so let's use the range formula now. Now we know velocity and we know our angle. We can start figuring out about how far downfield this thing's going to go. Well, range looks like this. Whoops. Our range formula is what? Velocity squared sine theta divided by g. Is that it? Velocity squared sine theta divided by g. I hope that's it, because if it isn't, I made a mistake. So let's put that in there. I know our velocity, so we're going to be equal to 27.86 meters per second, and we're going to square that thing, and then we're going to multiply it by the sine of about 43.4 degrees, because if this is 45 degrees, you subtract 1.6, you get about 43.4 degrees. And if you do look up, most hammer throwers do not throw at 45 degrees. They've actually found 38 degrees to be the best. So if we're going to divide that by 9.8 meters per second squared, and we're going to get a range of about, I came up with about 54.36 meters. 54.36 meters. So that's right here. This is where the ball is because the ball's let loose, not on the ground, but it's let loose about 1.9 meters above the ground, because the average person is about 1.9 meters. So if we just take the average, this ball is about 1.9 meters in the air already as it goes down there. So this distance right here is just going to be where it is at 1.9 meters above the ground. So this distance right here is going to be at where it is 1.9 meters above the ground. So it's got to travel some more here yet. So how are we going to find that out? Oh, well, we can get back to our basics to do that. Let's take a picture. All right, so this is going to be 54.36 meters. So we know now the ball is hanging out there at 54.36 meters. So let's see how much farther it's got to go. It's got to drop yet. Now there's several ways you can do this. I just chose the one we kind of get used to. Let's look at it this way. If we can look at this as being something that's going to drop from here to here. So I know my velocity final squared is going to be equal to my velocity initial squared plus 2 times AD. Well, I know D, I know A. I can find my final velocity. My velocity initial is going to be 0 because you're just letting it go. So my velocity final is going to be equal to 2 times A times D times the square root. My velocity final is going to end up being around 5.943, something like that. 5.943 meters per second. Now, why did I find that? Why do I care about how much it's going to take the final velocity as it hits the ground here? Because I can use that in the next formula, which is my velocity final is going to be equal to my velocity initial times plus AT, right? Now I can find how long did it take to go from here to there, all right? So my velocity final in this case is going to be 0, so my velocity initial will be what? 5.943 meters per second divided by 9.8 meters per second squared. You come up with seconds. My time it took to go from there to there would be about 0.0605 seconds to be precise. All right, so now I know that from here to here it takes 0.6 seconds. Well, how am I going to know how much farther it's going to come out here? Pretty easy. So we know this is the x direction. What is my velocity in the x direction as this is let loose? I have a velocity in the y direction. This velocity has. It has a velocity in the y direction, and then it also has a velocity in the x direction. This is the one I want to know. If I know this angle. I want to know the velocity in the x direction. So what's that going to be? Well, hopefully, hopefully it ends up being something like what? Cosine theta? I hope so. Let me see here. Yeah, we get that to be 20.4. So that'd be what? Cosine, that'd be velocity times the cosine of 43.4 degrees, and that velocity in my x direction, I think it comes out to be about 20.24 meters per second. So I know the velocity in the x direction is going to be 20.24. If I multiply it by that time, I should be able to find out what this distance is, because velocity times time is going to be my distance. And when I do that, it comes out to be about, this distance right here comes out to be about 12 meters. So if I add 12 meters to 54, I add 12 meters to 54, that comes out to be about 66.36 meters. And that is how far this hammer will go at this degree and spinning at a velocity of, I think we figured it out, 27. Our velocity is going to be 27.86 meters per second. And I know that my tension is going to be 2,550.73 newtons, which is about 573.427 pounds. So I know that if a person spins a hammer in such a way that it's 1.6 degrees less than what their body angle from their body, and we know if we let it go at 43.4 degrees, and we know if we let it go at this velocity, and we know we let it go at this velocity, it ends up over here at 54.36 meters, and we know we go from here to here, that's going to end up being 12 meters. This is going to be our total distance that the ball will go. Amazingly, most shot put are from 60 to, I think it's 60 to 80. Nope, you know what? I think it's 60 to 90. I think it's 60 to 90 meters. To 90 meters is pretty much the average. All right, so I hope that helps you. I mean, when you see physics problems like this, just remember, if you know a few initial situation, a few initial problem, or a few initial conditions is the word I'm looking for. If you know a few initial conditions with a couple of formulas, you can figure this out, a hammer throw. If you ever see this problem with a hammer throw, don't ever be afraid of it. Just look at these equations and you'll be just fine. I hope that helps you, and I hope you subscribe. See ya.